Okay, hello to everyone. Let's turn to our second lecture of today. The topic of the lecture is Introduction to Variational Inference. So it's a little misprint in the school program that you have. Because in this lecture we are going to discuss mostly some basics of variational inference approach and all questions concerning scalability of this scheme, application for big data set will be considered on the next lecture after lunch. That will be on scalable variational inference. We decided not to rush with this topic because variational inference is a very important theme. Actually, that is the key component of all modern Bayesian models. So it's important for all of you to understand this topic at a good level. Okay. Here in the school, we mostly consider a probabilistic model and do a Bayesian inference within them. In Bayesian inference, the most difficult task is to estimate somehow posterior distributions, because these posterior distributions involve some multidimensional integrals and it's hard to calculate them. Here is a couple of examples. The first is a very simple model. We have here a train set, test set, have some likelihood function of our data set given parameters theta, and also prior distribution of parameters for our model. And if we are fully Bayesian on the test set, we need to calculate the posterior distribution of the variables that we are actually interested in, meaning the test set, given everything that we know from our training set, the X train. And this conditional distribution can be expressed in this way. So we not pick just one model when we do our prediction, but mostly we average over all models in our set of models proportional to the posterior probabilities of these models given our training set. The other example is a bit more complicated. This is a latent variable model. And here we have some observed variables x, some model parameters theta, and also some hidden variables z that take part in our model but are not observed in our training set. And for this latent variable model, in training, people usually use EM algorithm. And in EM algorithm, we consider the incomplete likelihood function, the term that in most cases we can't calculate. Then we introduce the variance lower bound for this incomplete likelihood. This lower bound depends on theta of parameters for our model and also on some auxiliary variable q, some probability distribution over hidden variables. And maximize this ELBO with respect to both groups of parameters in a coordinate-wise manner. So on the M step, we fix our distribution q and optimize with respect to theta. And on the E step, we fix theta and optimize with respect to q. And it can be easily shown that the best answer is for q is just a posterior distribution of over hidden variables given our training set and parameter models. So here are two popular examples when we see that we need to calculate some complex posterior distribution. And so the main problem here is that this posterior distribution can be calculated analytically only for very simple model, which I call the conjugate model, the topic of yesterday practical assignments. Here on the deep Bayesian school, you understand that we want to consider mostly a probabilistic model that involves some deep neural networks inside them. And for such probabilistic model, nothing can be done analytically. These models are very difficult. So what we need now is to find some scheme, some algorithm in order to find or approximate this posterior distribution almost for any probabilistic model we want to use. And this is the topic that is called approximate Bayesian inference. Within this school, we will consider at least two major approaches for solving this problem. The first one is variational inference, the topic for today's lecture, and the other one that is called Monte Carlo Markov chain sampling, MCMC sampling, that we will consider later. As for variational inference, the main idea is actually very simple. Okay, first let's choose some let's say, simplified family of distribution, big Q. Say, normal distributions with unknown mean vector and covariance matrix. And then let's try to find the best variational approximate Q in this simplified family of distribution, minimizing some similarity measure between true posterior distribution and our approximant. As you know from yesterday's lecture, one reasonable way to introduce dissimilarity measure between two probabilistic distributions is just a KL divergence. So we can consider the following problem: minimize KL divergence between our approximator and true posterior within our simplified family of probabilistic distributions. So for now, it's not easy to see how can we actually solve this problem, because in this criterion function, we have as one of the components the posterior distribution, the thing that we actually can't calculate. So what we do now is to do some equivalent transformation in order to turn this criterion function into something that we actually is able to calculate. These transformations are very simple. So we just write down the definition of KL divergence and then write the posterior distribution as a ratio of a joint distribution and the marginal distribution of a data set. Then we split this log factor as a sum of three terms. The first term is actually something that we can calculate, because here states Q, which comes from our simplified distribution that we choose by ourselves. So this is something that we actually able to calculate. The second term, we can move out this log P of x out of the integral, because it doesn't depend on theta, and the integral over Q is just unity. So this is the factor, which is log P of x, that actually doesn't depend on Q of theta, the value we want to find. So this is just the constant that we can skip. And the last term is this one. And this is also the good term, because here states the joint distribution. The joint distribution, that is something that we know. Integrated with respect to Q, which is again come from our simplified family of distribution. So finally, our criterion function f is equivalent to this one. And if you look to this criterion function, this is something that is very similar to you, I guess. So if we take a minus sign here and change the minimization problem to maximization one, what would we obtain? Yes, just evidence lower bound, the criterion that we already used. So here, that is the same criterion. So we take the minus, change minimization to maximization, come to this criterion function, and this is just an evidence lower bound for this incomplete likelihood. This is easily seen if you take this inequality, take as an empty set as theta, rename z as mu theta, and this inequality will identically come to this one. And this is actually very good. So if we want to solve variational approximation problem, actually we need to solve very similar problem to that we solve within the EM algorithm. That is why it is easy to combine these two ideas together, the EM algorithm and variational approximation. So again, in conventional EM algorithm, we have this problem, evidence lower bound, which is maximized with respect to two groups of parameters. So if we try to use within EM algorithm the variational approximation idea, what we do, instead of this step, on the E step, we try to find a variational approximation to our posterior distribution. But for finding variational approximation, we need to optimize the same criterion function. So now we can unite these two ideas into one actual optimization problem. This is the same evidence lower bound as it was here. The only difference is that we maximize with respect to theta and over probability distribution Q, which are taken in some restricted family of simplified distribution. nothing more. Okay, as you remember, the conventional EM algorithm has some guarantees on finding a stationary point of our incomplete likelihood after his iteration. What we get in the case of variational EM? Again, here the formulation of variational EM, and here the picture that you already have discussed for conventional EM algorithms. Here the green line is our incomplete likelihood with respect to theta. And what we do on the E step and if step is the following. On the first step, with our initialization of parameters theta and our variation approximation Q, we introduce the lower bound here. And on the E step, try to maximize this lower bound to make it tight. In variational EM algorithm, this is certainly not possible because we are not able to find the true posterior distribution here, and that is why we have some gap which is determined by the value of KL divergence between the true posterior distribution and our best variational approximation. So we make our variational lower bound that is not tied to the green curve. However, for this new lower bound, we are able to maximize it with respect to theta. In this new theta, construct a new lower bound which is not tight and continue till convergence. And as you might guess on this picture, this algorithm again will converge to the local maxima of incomplete likelihood. Unfortunately, there is no theoretical guarantee that this would be true for all cases. In variational EM algorithm, we are guaranteed that we find a stationary point of this variational lower bound and not the true incomplete log likelihood. But in most practical cases that you face, this will be true. It's really hard to find examples when this variational EM algorithm will not lead to solution. So that's usually a standard recommendation that if you are not able, even if you are not able to make the exact E step, you can still use a variational EM algorithm for training your model with latent variables. Okay, another thing that it is important to discuss is some interpretation of this ELBO criterion function. So what is actually going on when we try to optimize this criterion function? Again, let's consider this simple model, and we want to find the approximation to posterior distribution Q, and in this way to maximize this evidence lower bound. Now let's do some equivalent transformation. On the first step, we write down that the joint is just a product of the likelihood and prior, so the log of joint is just a sum of these two terms. And then let's unite the last two terms into one expression. And so we have finally the sum of these two terms. The first one is the log likelihood function averaged by our posterior distribution Q. And the other term is actually the minus KL divergence between the prior distribution and our posterior approximation Q. So we can interpret our ELBO criterion function as a difference of these two terms. The first term we can call the data term because this is the only term where our data are used, X. And this is the KL term, the difference between prior distribution and our approximation Q. Now let's throw away this second term and optimize only the first data term with respect to our approximation Q of theta. And in this way, it's easy to see that we come to just maximum likelihood approach. If we maximize only the data term with respect to distribution Q, the answer is just delta function centered at the maximum likelihood point, nothing more. If we return to to this criterion function and consider two terms, what we do, from the one hand, trying to find the best Q, we want to find the Q that best explains our data, that maximizes our log likelihood. And from the other hand, simultaneously, the chi-L term here goes with minus sign and we take maximum, we want to be not far from the prior distribution. So here we make a kind of a compromise in finding Q. We want to find the Q that simultaneously good explains our data and not far from our prior distribution, from our previous knowledge about this setup from previous experiments. So this is rather a reasonable idea. And imagine that you have a huge data set, a huge number of points. And in this case, the data term overweigh the KL term, dominates it. And actually, our variational inference scheme would just turn to the maximum likelihood. And it's okay if you have a huge number of data comparing to the number of parameters that you need to calculate, just use this data, use ML approach, and this is the efficient way to do the inference problem. If you have not a lot of data comparing to the number of parameters you need to estimate, you need to somehow balance your data with some prior knowledge about your parameter. Okay, so now it's time to discuss this big Q simplified family of distribution. Which distribution are actually simple that we're actually able to maximize this ELBO criterion function within them. We will consider two classes of this variational distribution, and the first one is called mean field approximation. Actually, the variational inference methods originally comes from statistical physics area, and the first really effective approximation family was this one, mean field approximation. That is one, this is physics terminology here. So what distributions are actually simple? One way to introduce simple distribution is to do the following. Let's take our vectors of variables theta and split it into non-intersecting sets, subsets, theta 1, theta 2, theta m. So the union of this theta I is the whole set of theta, and they are not intersecting. And then suppose that in our variational distribution, different groups of variables are actually not correlated. They are not they are independent. In extreme case, we can say that all variables in our distribution are independent. This would be very simple distribution. Every integration with respect to this distribution can be easily calculated. Okay, and then let's try to maximize our evidence lower bound within this family of distribution, again in a coordinate-wise manner, like in EM algorithm. So on each iteration, we fix all the factors here except for one, and then optimize this ELBO with respect to this factor Qi. Note that this is a variational optimization problem. Here we need to find a minimum of this criterion with respect to whole family, all possible family of probabilistic distribution. It's a variational optimization. That is why this approach, this family of algorithms is called a variational inference, even in the cases when there is no variational optimization inside it. Because originally it has come from these ideas. And it is actually quite difficult to solve a variational optimization problem, especially in closed form way. However, fortunately for this particular case, we are able to solve this variational optimization problem analytically. So what we do, we just take this criterion function, put our family of distribution here, and make a set of equivalent transformation. I don't think they are very simple. I'll skip a bit. I don't think that it's too important to discuss them in detail. I just wanted to come to the answer here that after this equivalent transformation, it is possible to show that our criterion function is just as constant with respect to our Qi, the factor that we optimize, minus KL divergence between this factor Qi and some probabilistic distribution that depends on all other factors that are fixed on this iteration and our data term. And we want to maximize it with respect to this Qi. So this is evident that the answer for this optimization problem is when these two distributions actually coincides. So the answer, the optimal value of the factor Qi is this distribution. So what we need to do here is to take a log of a joint distribution, to marginalize it with respect to all factors that are fixed on this iteration, take an exp and take a normalizing in order to be distribution here. So some analytical formulas. And in this way, we come to the following general scheme for mean field variational approximation. So what we do, we fix our factorized family of distribution and initialize it somehow. Then, in a loop for each factor, we do recalculation of this factor, giving all other factors fixed, using this formula that is derived on the previous slide. Do it for each factor, then we calculate our ELBO criterion function. This ELBO actually involves integrals that are very similar to the one that are needed to make a recalculation, and repeat. Do this until convergence of our ELBO criterion function, which we want to find the stationary point. The main assumption that we actually make here in order to make this algorithm to work is that integrals that you see here are actually can be calculated analytically. Because otherwise we just can't work with distribution, arbitrary probabilistic distribution. How is it possible to assign this thing? If we can derive some analytical formula, say this factor is some gamma distribution with unknown parameters A and B. So what we do in this iteration on computer, we actually recalculate these parameters A and B on each iteration. But if we do not have a closed form solution for this Qi, we even can't assign the value for this arbitrary probabilistic distributions that is stated here. Okay, you might ask the following question. Here, as you see, states the integral, the multidimensional integral, with respect to all model parameters except for one factor. If we consider the calculation of posterior distribution, there also states some integral with respect to all model parameters. So here and there, this similar multidimensional integral. How is it possible that we can't calculate the true posterior distribution, but in the same time, we are able to run this algorithm? And the answer is that, yes, there are a lot of situations in many probabilistic models that calculation of such integrals is much, much more simpler than the calculation of integral of this kind. You might know that here states the log of a joint distribution and not the PDF function itself. And this is very important because, say, for example, our joint distribution is multivariate normal distribution with respect to both groups of variables. So if we take a log of a joint, it would be a quadratic function. There would be functions that involves only linear terms and some quadratic terms. And here, to calculate this integral, you just need to estimate a mean of this distribution and the covariance matrix, nothing more. But here states the probability density function itself. So here, for example, if this is multidimensional, we need to find an integral with respect to the PDF and normal distribution itself. And this is much more difficult problem. Okay, in order to just give you a simple example of more or less practical probabilistic models that actually use this mean field variational inference scheme, I suppose to consider, I would say, one of the most popular Bayesian model of all times. This is called a latent Dirichlet allocation model. By the way, how many of you are familiar with this model? About a half of the room. Okay, so I quickly give an overview of what this model is about. This is actually really one of the top-cited articles of all times in computer science. This model has a huge number of extensions and modifications, and actually is a cornerstone of topic modeling research area. So LDA model is some tool for topic modeling. In this setting, we have some collection of documents, some collection of text, and we want to describe them in terms of topics, which topics are covered by this document. And in the simple case, LDA model do the following assumptions about our collection text. The first assumption is so-called bag of words assumption. We just say that each document is a collection of words, regardless their order in the sequences. So just a bunch of words. The second assumption is that each topic is just a probability distribution, some probability distribution over a set of all possible words. Here on example, you see some topic with probabilities for the words gene, DNA, genetic, with some high probabilities, and almost zero probabilities for all other words in the vocabulary. So we might interpret this topic as some topic about genetics, and so forth. And the last thing, the last assumption of LDA is that each document probably consists of several topics. So it's, in terms of mathematics, it's a discrete probability mixture of several topics. And using this assumption, the generative process for one document is actually the following. First, we choose the topic probabilities for one particular document, the probabilities that this topic is within this document. This is theta, from some prior distribution. Then for each position in the document, we first generate a topic assignment using this probability setter, and the topic assignment is z, some discrete variables. And then we generate the particular word in this position using some probabilities of this word within the selected topic zi. So very simple, and what we want, if we have a collection of documents, we want to estimate somehow these probabilities of words in each topic, and also these assignments of topics within each document. In mathematical terms, if we consider just one document for simplicity, we come to the following probabilistic model. So we start with the joint on our document, so the collection of words W that is observed in our training set, then hidden variables Z, that's the topic assignment, the probabilities of each topic in this document, and we have two parameters. Parameters phi, the probabilities of each word in each topic, and additional parameters alpha that controls the prior distribution over theta. And in this probabilistic model, we have three groups of factors, two discrete distribution, this distribution of topic assignments and words assignments, and also we need to, if we are Bayesian, to put some prior distribution over theta, where theta is the probabilities for each topic. So the probabilities actually lies in the probability simplex. So here we need to put some distribution over probability simplex. And the simplest distribution that you might know over probability simplex is just a Dirichlet distribution, and this distribution is also good because if you choose the parameters of this distribution in the right way, you can easily put most of the mass of distribution to the corner of the simplex. It means that in a probable situation, most of the values that are generated from Dirichlet distribution would be close to 0. It means that in our document, there are only few number of topics that are probable, and all other topics are not. Very reasonable assumptions about topic distribution within the document. In a similar way, we might introduce some Dirichlet distribution over this phi, the distribution of words within each topic. Okay, so we have this probabilistic model. This is the probabilistic model with latent variables, because we have observed variables W, 2 groups of hidden variables, and some parameters of models. And as you might see here, it is impossible to derive the true posterior distribution over Z and theta given all other parameters because of this factor. This factor hooks in not trivial way these 2 groups of variables, real values theta and discrete variables Z, and because of this factor, you actually can't find the closed form solution for the posterior distribution of these groups of parameters. So what to do? To the current moment, we know only one approximate Bayesian inference algorithm, that is a mean field variational approximation. Okay, let's try to apply this. So we, as always, consider the ELBO maximization problem and put our factorized assumptions on the family for Q, for posterior approximation. The posterior assumption that actually these 2 groups of variables, Z and theta, are not dependent within this distribution. And now let's just apply the standard mean field variational formulas to find the formulas for recalculation Q of theta, Q of Z. So if I just remind you here, so what we need to do, we just need to take a log joint to integrate it with respect to all other factors, take an exp and normalize. So that is what we do here. So we consider the log of our factor, new factor Q over theta, and this is calculated in the following way. We take the log joint of our distribution, marginalizes with respect to all other factors fixed, and all other factors is just Q over Z, nothing more, plus some additive constant, normalization constant. Then we use this factorization for our joint distribution. This is the product of some factors. That is why it's very good to come to the logarithm in order to get a sum of these terms. So here we have three terms in the sum. The first one actually doesn't depend on Z at all. So this is the log of prior distribution over theta. Then comes some factor that somehow interacts this Q over Z and the theta value. And the last part, this one, is actually does not depend on theta at all, so we can write it as a constant. And what we do next, here we just write what is log of Dirichlet distribution. This is just a sum of log of separate theta times some coefficient, and also write what we get here. And after equivalent transformation, we come that the new distribution Q over theta, the logarithm of this distribution, has the following form. It is the sum of log over theta t times some value plus a normalizing constant. And looking at this expression as a function of theta, it is easily seen that this is just a Dirichlet distribution, but with some modified parameters here. So if we take an exp here, so that would be a product of theta and some powers, the same like here. So we just denote this as a new parameter, gamma, and say that our new Q of theta is a Dirichlet distribution over theta given some gamma, which are calculated using distribution Q over Z. So what we really do this here is, we say that, yes, we can calculate the posterior distribution over two groups of variables, of theta and Z. But if we fix one set of variables, the model actually becomes a conjugate model, and we are able to write down the distribution in the closed form. This is also called the conditional conjugacy of the model. Yes? Okay, here. Here just indicate a notation. So if the expression is true, it equals to 1. If it's not, that is 0. And again, in the same way, it is possible to derive the closed form solution for Q over Z. I will not write down this formula, but this is very simple. Okay, now we have the first approximate Bayesian scheme, mean field variational approximation. As you see, this is not a general solution. Certainly, it is possible for some models to use the scheme, but we require for our model a property of conditional conjugacy. That if we fix some group of variables with respect to other variables, we are able to derive analytical formulas. Certainly, this is possible to apply only for a restricted number of distribution. And in this way, we need to somehow enlarge our approach, variational approximation, to some other probabilistic models. And in this way, we can consider the second family for big Q of simple distribution, which is called just parametric variational family of distribution. So we say that our variational approximator is just taken from some parametric distribution, say from multivariate normal distribution with some unknown mean and covariance matrix. And in this way, if we take again our ELBO criterion function and put this parametric assumption here, we come to the following optimization problem, which is here is not more a variational optimization problem. It's just a normal parametric parametric optimization problem where we might try to use some numerical optimization solver for solving this. And in order to do this, we need to find a way actually to calculate this criterion function and the derivative of this criterion function with respect to the variables that we optimize. And here, this is a lambda and theta. So if we are able somehow to estimate this expectation and to estimate the gradient of this expectation with respect to lambda and theta, we just put it into your favorite optimization solver and we are done. Again, in this description, this is not possible to do in a general setting for all kinds of probabilistic model you might imagine. But it is possible to do for some models that are not covered by mean field approximation. So let's see some notable example, which is a Bayesian logistic regression. So the Bayesian variant of logistic regression model. So here we consider just a two-class classification problem and try to train a linear classifier for this problem to find some weights W. And our probabilistic model is the following. We introduce the joint distribution over class labels and our weights W as a product of two terms. The first one is the likelihood term as in normal logistic regression model. So this is the product of sigmoid function over linear combination of w times x, I. And also, since we have some parameters w, which in Bayesian approach we interpret as some random variables, we need to put some prior distribution over these parameters. Prior distribution that encodes our understanding of what parameter values are good or bad for this model. And here, one reasonable assumption about this prior distribution is the following. Just take a normal distribution centered at 0 with some covariance matrix. So we say that from our prior assumption, it is preferable to have these weights W closer to 0 in L2 norm. The closer it to 0, the better is the model. The simpler is the model, the less overfitting we can observe for this model. But we don't know the particular variance, how far we can move from 0 and to get a good model. So we put here parameters that we are going to train during training of our algorithm. So we have the following model, which is called Bayesian logistic regression. And this is the latent variable model. So we do not think on what we are doing, just take variational EM algorithm, take incomplete likelihood, take ELBO criterion function, which can be written like this, and maximize it with respect to what? With respect to this parameter of our model, and with respect to distribution of our hidden variables W. As you might note, here we can't use a mean field approximation. Because if we say that, okay, that Q of W is just independent distribution over each component of W, this doesn't help us. Because here we need to estimate the expectation over this factorized distribution over log joint. And in this log joint, we have a log of a sigmoid function. Log of sigmoid function times some distribution over W. And you just can't calculate such kind of integrals in a closed form, even if this Q of W would be a normal distribution. And also, this Q of W, this should be, in ideal case, a posterior distribution. So it's not quite reasonable assumption that all the components in this distribution is actually independent. So let's do the second approach, parametric variational approximation, just to choose some parametric family for our approximant. Let's take a multidimensional normal distribution with some mean vector and covariance matrix. So we have some covariance here in this approximation Q, and try to maximize our evidence lower bound with respect to these variational parameters, mu and sigma, and also with respect to the parameter of our model alpha. So here we can write down again our ELBO criterion function. This derivation is in view of data term and KL term when we discuss it, when trying to interpret ELBO lowest bound. Okay, we have these two terms. The second term is just a KL divergence between two multidimensional normal distribution. And this thing can be just calculated analytically. There is a closed form for this expression. So here we just write down something very simple. The more interesting part is actually states here. So first, what we do, here the log likelihood, and this is a product over a separate object. So this log is actually a sum over object of individual likelihoods, and we need to take an expectation with respect to multidimensional normal distribution. Then we put that here actually states the log of sigmoid function. This is again analytical expression. And this expression actually can be calculated in the closed form because this is the log of a logistic function times some normal distribution. So what to do? That is the place that I say that this parametric approximation family works only for some subset of distribution. So you need to take your particular model to try some variational family of distribution and try in some ad hoc manner to estimate the things that you actually face with. Okay, let's do this for this particular model. The first note is the following. Here, the function that states here depends on W only through this linear combination. So here states the multidimensional distribution, the huge number of dimensions, and here just stay a real value. And it is easy to show that if some variable has a multidimensional normal distribution, then its linear combination with some fixed weights, it is a sum of normally distributed random variables, is again normally distributed. And we can write analytical expression for this. So this number, real number, linear combination, is just a normal distribution with some parameters that are calculated analytically. So in this way, we change our multidimensional expectation, a huge integral, just to one-dimensional integral over the normal distribution with some known parameters mean and variance. Then we can do the further simplification. We can generate some random variable from normal distribution in the following way. We just generate some standard normal distribution and then shift and scale it using our mean and variance. And in this way, we can generate our arbitrary normal distribution. So let's do the same thing here. So change the expectation with respect to some normal distribution to the expectation with respect to standard normal distribution, and change instead of UI this expression as expression of CI. So finally, we come to the following expression of our evidence lower bound. This is a sum over all object in training set. Some one-dimensional integration over standard normal distribution, and some analytical expression here. And we need to calculate the gradient of this criterion function with respect to all parameters that we optimize, meaning the mean vector, the covariance matrix, and the parameter alpha. Okay, let's calculate, or at least to show how to calculate the derivative of this criterion function with respect to mu. So here states the sum of object, a linear operation. Then an expectation with respect to some fixed distribution, also a linear operation, and a derivative, which is also a linear operation. So we can change the order of this operation. So we move this gradient with respect to mu inside this expectation. And here states some analytical expression, so we directly calculate this derivative. So, and in the same way we can do with sigma, alpha, etc. So what we actually need to solve this optimization problem, just to calculate this one-dimensional integral with respect to standard normal distribution, here and here for this expression log of logistic function and its gradient with respect to some parameters. And since this is a one-dimensional integral over some standard probabilistic distribution, we can use any numerical integration solver you want. Since we here take an expectation with respect to normal distribution, a good way is just to take a Hausser-Mead quadrature, but other methods, other approximation numerical integration schema are also possible here. So this is the very fast operation, just to take a sum over some points perfectly chosen. Okay, this was the second approach, and again, the main problem here is that this approach is not generate. So what we've done, we've taken some particular model and look at all components in this model, and with each component do its own thing. Here we calculate something analytically, here we make this transformation using some very specific properties of normal distribution, and actually find to some, come to some good algorithm, but it is possible only for this particular model. If you take some other model, which involves possibly some neural networks, you can't do the same thing. So the next step that is actually will be solved already in the next lecture after lunch is to find some procedure that will be even more general than this one that we described in this lecture. Okay, so now, because you haven't asked me any questions during the lecture, we have finished less than an hour. Okay, let's summarize everything that we're talking about. So first, we discussed today the variational inference approach, some approximate Bayesian inference scheme. And in this scheme, we transform the Bayesian inference problem into just optimization problem, some certain class of optimization problem. And in this way, solving optimization problem is usually much faster than generating some samples from distribution. So variational inference approach usually works very fast, okay? At least comparing to some other approaches like MCMC. Then the second thing that you should note is that, at least till now, variational inference is not a general scheme. We have discussed two kinds of approximation for simplifying distribution: mean field approximation, some parametric approximation, and also we may use some combination of these two approaches. But this is, say, ad hoc approach that you should use looking at your model and trying to find the properties that you have in your model. The next thing is that when we do this simplifying assumption on our posterior distribution, this assumption could be rather poor, because what we do is from the one hand, we try to find a posterior approximation in quite rich family, but from the other hand, we need to take only those family for which we are able to calculate all the integrals, all the expectation, etc. So if we consider, say, a factorized family of distribution, so if we ignore some correlation between two groups of variables, it might be a poor approximation for the true posterior distribution. However, at the training phase, when we use this variational approximation within variational EM algorithm, usually it works. So the final value of model parameters that we find using variational expectation optimization algorithms is usually the same as if we use the conventional EM algorithm with true E-step. So the normal recommendation is to use a variational inference scheme at the train phase, when you learn the model parameters, and to use some different, more accurate scheme for approximating posterior distribution on the test set, when you want to find the posterior distribution for one particular testing object with all the correlation properties, etc., within it. And the last point is that here in this lecture, we haven't discussed any scalability issues. What we do if we have a huge training set, a lot of number of parameters, a lot of number of parameters within theta. So if we transform in variational inference our Bayesian inference problem to optimization problem, is it possible to transform it not just to optimization problem, but to some kind of stochastic optimization problem in a way to use stochastic solver that are usually very good for big data set? In some cases, it is really possible, and that is the topic of the next lecture after lunch. Thank you. Okay. Different approaches here are possible. So we speak about variational EM scheme for mean field approximation. So if we use the mean field approximation within the variational EM, we have an optimization with respect to these groups of variables that states here, and also with parameters that we recalculate on the M step. And the question is in what sequence to do the recalculation, to do just one pass over all factors and then one pass over the parameters of the model, or to fix the parameter of the model and do a lot of passes here for the convergence to the current posterior distribution and move further. If we speak about general situation that works for most problems, usually people do just one pass over factors here and then do some pass or do M step, exact or approximate. Because what we actually do here, we just maximizing our evidence lower bound with respect to all groups of variables. So if you consider some coordinate-wise optimization methods for some general criterion function, usually we optimize with respect with each group of variables, and then so it's more beneficial to try different groups of variables than to optimize with respect to one bigger group of variables than other one, etc. So usually the usual practice is to loop over all groups of variables and then loop again. And here we do not have any loop. Here we have some just a gradient thing. So we calculate the gradient function and use it in the gradient descent on LBFGS on what you want. Here we do not consider the stochastic optimization thing. In stochastic thing, when we calculate this sum over mini batches or something, this is a bit different thing. But this is the topic for the next lecture. But here we just calculate once this gradient and make a move over all variables. No. Here we do not have E step and F step. We have just one criterion function, 3 groups of variables, and the gradient optimization with respect to all of them. So we calculate once the gradient of this function with respect to all of these variables and change them simultaneously. We do not loop over them. Okay, you mean this one? Okay, and what's the question again? No, because in order to calculate this gap, you actually need, this gap is a KL divergence between the true posterior and our approximation. So you need to know the true posterior in order to calculate this. Sometimes you can use some estimation to this gap, but not the true value. What do you mean by approximate Bayesian evaluation? Well, I haven't caught all your words, sorry. So if you, I said that if we consider some sampling scheme for approximate Bayesian inference, this scheme usually takes much longer time comparing to variational inference, because in variational inference we're just solving an optimization problem, some gradient optimization, and we do not do sampling. Each sampling takes more time than some simple calculation. If you speak about some other similarity function here, yes, it is possible not to take KL divergence, some other alpha divergence family, and also to change this to distribution to because KL divergence is not symmetric one, to put Q here and posterior distribution here, and it is a different approach that is called expectation propagation. Other approximate Bayesian scheme, but we do not cover in the school because now it is not really popular, quite widely used. Okay, everyone want to lunch? Okay, if you have any question, please come to me and also to you. And okay, go to lunch.